Good afternoon and welcome to today's special session of the IARPIC Arctic Data Collaboration Subteam meeting entitled Towards a Data-Driven Quantitative Social Science. My name is Timothy Pash. I'm Associate Professor of Communication at the University of North Dakota and PI on an NSF Arctic Social Science Award conducting fieldwork in Nunavut and Alaska. I would first like to thank Jonathan Blythe and Michael Brady for inviting Dr. Gary King of the Harvard School of Government to deliver today's presentation. Thank you also to Anne-Christine Zinkan for her considerable logistical support and the opportunity and scholarly privilege for me to provide a brief 5-minute introduction for Dr. King. Dr. King is the Albert J. Weatherhead III University Professor at Harvard University, one of only 25 with Harvard's most distinguished faculty title, and director of the Institute for Quantitative Social Science. Dr. King develops and applies empirical methods in many areas of social science, focusing on innovations that span the range from statistical theory to practical application. Dr. King has been a member of the Senior Editorial Board at Science, visiting fellow at Oxford, and senior science advisor to the World Health Organization. He has written more than 175 journal articles, 20 open source software packages, and 8 books. His replication article initiated the data sharing movement in political science, and his ongoing international Dataverse project supports the data sharing movement across fields. Dr. King's work is widely read across scholarly disciplines and beyond the academy. He is regularly included in lists of the most highly cited researchers across the social sciences. The goal of today's Arctic Data Collaboration Subteam meeting focuses on how different sectors in society can contribute analytical capacity and proprietary data assets to best advance the Arctic research enterprise, while protecting individual privacy and data sovereignty. Dr. King's presentation today, Statistically Valid Inferences from Privacy-Protected Data, synergizes closely with topics from a recent NSF Arctic Data Center workshop that I would like to mention briefly prior to Dr. King's talk. In those workshop discussions over several days this past April, building on some of the insights shared in the Arctic Horizons Report of 2018, researchers discussed the many challenges facing Arctic social scientists with respect to data sharing and reuse, including working with sensitive and privacy-protected data many of us are unable to share or use for collaboration. As we look to determine ways forward to mitigate those and other Arctic social data-related challenges while fully protecting participant privacy. Dr. King's work addresses a number of these recommendations, and his methodologies suggest significant applicability to Arctic social sciences. If statistically valid inferences from privacy-protected data may be realized in accord with human subjects, privacy and data sovereignty agreements, this would be highly significant as a development in terms of Arctic social scientific collaboration, data synergies, and enhancing capacity to better leverage broader impacts for addressing grand challenges in the Arctic region. I will conclude my introduction by referencing a recent presentation video Dr. King recorded for a US federal interagency conference on social science and big data, where he asks the question on many of our minds: how do we empower the social sciences to understand and ameliorate major challenges of human society? In answering this question, Dr. King engagingly describes 3 critical elements for empowering social scientific researchers. He describes the importance of enhancing connections between different sectors of society, ranging from government to academic to industry, and finding ways to connect our work between data sets. He describes the importance of methods, focusing not only upon the data itself, but especially on new innovations in analysis, new methods, and social data analytics, turning big data into actionable insight. And finally, Dr. King describes the importance of enhancing our ability to ask the right questions, realizing that the data is not only there to answer the questions we already possess as preconceived notions a priori, but rather that we be ready to see how the data can, in and of itself, suggest new questions to us if we are open to them. Thank you so much, Dr. King, for generously sharing your insight with the IARPIC Arctic Data Collaboration Subteam today. It is a privilege to turn the floor over to you. Thank you once again, Dr. King.
Thank you, Tim. I really appreciate it. And thank you, everybody, for coming. I am going to do the official thing and share my screen while we speak. But I'm not making it so I can't see everybody. I have a big enough monitor so I can spot you if you're hiding. In fact, if you'd like to share your video, that would be great, because it's nice to have feedback, even just murmurings or like this or whatever. But feel free to do whatever makes you comfortable. This is a talk. Let's see. Let me just arrange my screen here so you are not in front of it. There we go. Okay. Great. I'm really excited about this. I think that it was a great invitation, and I'm thrilled to be here. The point of the paper that I'm going to describe today is about an attempt to solve a political problem of data sharing technologically, but we want to do it in a way that doesn't annoy the researchers that we're going to provide the data to. So it's not always easy to do that, and that's what we're going to try to figure out. So this is statistically valid inferences from privacy protected data. Georgie is my graduate student. Meg is my graduate student also, but she just took off some time to be Joe Biden's chief data scientist, actually. And Aberdeep is at UCSC and also at Google. So here's what our story is. So I'm going to tell you about solving political problems technologically. I'm going to talk about a particular method of solving political problems technologically, which is differential privacy. Will enable us to share data in a way that absolutely mathematically protects the privacy of individuals or firms or whatever it is we want to protect, but at the same time makes it possible for us all to analyze the data and find patterns in it for public good or for good government purposes or whatever it is we're seeking to do. So that's going to be the goal. But I want to start off with an example of how we convinced Facebook to make its data available, because convincing companies and governments and others to make data available to academics and to each other is actually really important. The United States Social Security Administration does not share data, will not share data with other parts of the United States Social Security Administration. And then obviously if they did that, they would make faster progress. And if they shared data more with the academic community, we would all probably have more secure retirement accounts. And it's not limited to them. It's limited. It's also, the problem also exists inside private companies sharing with each other and from any company sharing data with academics so that we can make some progress. And I find that in government, you guys can hire people that I couldn't hire. And in companies, they can hire people that neither of us could hire. But I can hire people that probably you guys couldn't hire, like somebody that wants to spend 6 months proving a mathematical theorem, and Facebook couldn't hire them either. Working together with a flow of information back and forth with the different types of people that want to work in different places actually makes us all better. So that's really the goal. It's to have the flow of information. And so this invitation, I think, may actually produce some other kinds of progress. And then also having data flow so we can all use our different analytical techniques. So I wanted to convince Facebook to make data available. This is solving a political problem technologically, and the technology is basically constitutional design. So I had been trying to convince Facebook for some years to make data available, and I was out there, as I had gone many times, to try to persuade them. It wasn't a particularly successful trip because I had taken lots of previous trips and they were not particularly successful. And so I'm in my hotel room packing to go home, and I get this email from them that says, "Hey, what do we do about this?" And this was Cambridge Analytica, which is like the biggest disaster in privacy protection that had existed until then. So this was pretty much the worst timed lobby event like in the history of the world. So I thought, fine, I'll just pack, go home. I had a fine time out in California. But 3 days later, they called me, Mark Zuckerberg called, and he said, hey, could you do a study of the 2016 election and tell everybody that we didn't change the outcome? Or maybe if we did something wrong, like tell us what it is and we'll fix it. You know, losing $100 billion in market cap sort of focuses the mind, you know? So I said, I'd love to, but I need to do two things. I need two things from you, and you're only going to give me one thing. So one of the things is I need, of course, complete access to the data and the people and the platforms and everything, just like employees have, right? I need complete, otherwise how could I do the study? But second, I need something that employees never get, which is no pre-publication approval by the company. Right, because otherwise, because then even if they let me publish the article, it wouldn't be of any use to the academic community, right? They're only going to let me publish things where they come out looking good, right? It seems crazy, right? So he said, oh, you're right, we can't give you both of those things. I said, well, okay, then I'm not doing the study. And he said, well, no, I want you to do the study. And I said, well, okay, give me both of those things. He said, no, we can't give you both of those things. I said, well, okay, I'm not doing the study. And so we went back and forth like that a bunch of times. And until I finally said, wait a second, here's a solution. So instead of giving me both of those things, data access and no pre-publication approval promises, we'll have two groups. One group, outside academics, will apply for access will say what they're going to do, just like if you apply for government data, you have to say what you're going to do ahead of time, and only certain proposals are approved. And the company would have no veto. These are the first academics that would have the ability to publish with no prior approval by the company. However, the people that would approve whether or not they have access is not Facebook. And what it is a trusted third party, a bunch of academics at a commission, forming a commission at a group I created called Social Science One. And those people, those senior distinguished academics, sort of take one for the team. They agree not to publish at all. They learn all the inside secrets in Facebook relevant to this problem, and they make the decisions about which academic proposals are meritorious. However, if somebody says, I want to study this subject, and it's a great subject, and it makes sense, and it's within the scope of what Facebook said was okay, which, by the way, is the effect of social media on elections and democracy. But it happens to cross the paths of a lawsuit that is secret, that someone's suing Facebook about. And if we said yes, that they can analyze that, then those researchers would be deposed for the next 2 months. We would say no, right? And so we would deny the proposal, even though it was a great proposal. So that protects Facebook and it protects them. So this proposal worked. So the cool thing is that the problem was solved with no balancing of interests. We didn't have to violate somebody's privacy in order to create public good. Everybody got what they wanted. There were agreements signed, there were big announcements. Mark Zuckerberg testified before Congress around then, and he described this whole program. 30 plus people at Facebook, full-time people, were assigned to our project. Everything was great. There was just one issue. And that was Facebook's implementation plan was like utterly illegal. They didn't know this, and they were completely well-meaning and were really trying. But the privacy protections that they had in place inside Facebook, were not adequate to the task. And so it really wasn't going to work. So now we had a new problem that we had to figure out how to solve, which is how to share data from Facebook without it leaving Facebook, because it's not allowed to leave Facebook. So how do you do both things that seem completely incompatible, right? So that's the question. And so the solution to that was going to be, is this idea of differential privacy that I'll describe. By the way, anyone that wants to interrupt me is perfectly welcome. I would welcome interruptions, or feel free to yell out obscenities or whatever it is the custom in Arctic research. You can just there aren't very many of us, so feel free to just unmute yourself and say hey. Okay. In any event, so we needed to solve this problem of sharing data without it leaving Facebook. How are we going to do that? So it turns out after study that we concluded that we're part of a big movement, really, and we would use that movement in this case. And the movement is from a data sharing regime to a data access regime. And what I mean by this is another political problem solved technologically. A data sharing regime is, I give you my data and maybe you sign a data use agreement. That's the whole thing. And then there's going to be a data access regime. So let me explain both of these. The data sharing regime, which we've been doing for years, is venerable, right? But it's failing. It's failing. Well, why is it failing? Because there's enormously increased concern with privacy among academics, because scholars in computer science have utterly ruined the day of us social scientists. They discovered that de-identification, which is the main way that we have protected privacy, it really doesn't work. It actually doesn't work. You eliminate somebody's name, address, and telephone number and other identifiers, you can still re-identify somebody. It's not hard. LaTanya Sweeney demonstrated that with 3 facts, we can re-identify 87% of the United States population. 3 facts: their state of birth, their gender, and their zip code. That's it. That's all you need to know. And almost all data sets we have are far more informative than that, right? And so de-identification doesn't work. Nor does a lot of the other solutions that have been tried. Releasing aggregate statistics, auditing the queries you're allowed to ask, having data clean rooms, having legal agreements, having restricted viewing, paired programming models, et cetera. None of that worked. And it turns out even trusting researchers fails spectacularly at times. That's what Cambridge Analytica was, right? Because that was actually a researcher. That pisses me off. And it turns out mathematically that trusting a researcher known to be trustworthy can fail at times as well. So like the whole thing's a big mess. What do? Instead of giving someone a data set and hoping that they will treat it appropriately, instead we're going to give them a server. We're going to give them access to the data under very specific conditions. A trusted server holds the data. The researchers are treated as adversaries. That annoys me too, right? I want to be trusted, but the researchers are treated as adversaries who are trying to violate private data, and everything we do will prevent that. The researchers can run any method, any statistical method they want, and instead of getting back the normal answer on the original data, they will get back a noisy answer. And where noise is added in a very specific way, a minimal amount of noise, such that it is impossible to violate anybody's privacy, no matter what the query run, no matter what the statistical analysis run is. And that's the basic idea of the data access regime. However, there's only a limited number of times you can run it. Otherwise you could run it a whole bunch of times and average away the noise, and so they won't let you do that. So the goal of this technology is to make it mathematically impossible to violate any individual's privacy, but still make it possible to analyze the data and find population level patterns. Because in the social sciences, that's what we care about, right? We, for the most part, we don't care about anybody. We only care about everybody, right? Those are the kinds of patterns that we're interested in. And the differential privacy enables us to solve this problem, to not violate anybody's privacy at the same time as we make it possible to discover population level patterns. Yeah.
Sorry for interrupting.
No, that's great.
Yeah, I'm really interested in the implication of the limited use of data, because that it sounds like that nobody can ask a similar question after that one researcher has conducted their analysis? Or is there ways to slice and dice the data that you could ask numerous questions that are related?
The way it works, and I'll show you a little bit of how it works, is there's a certain amount of privacy that any data holder would be willing to provide, would be willing to give up. And you don't want to give up enough so that any individual their privacy can be violated, of course. But there has to be a limit. Otherwise, you can run enough analyses to get past whatever the problem is. So, but all the results presumably would be public. So you could run the same analysis again. You would get exactly the same results. You could say that we want a less noisy result, and you would spend some of the privacy budget. There's literally a notion of a privacy budget. You would spend more of the privacy budget on a particular thing. But the difficulty from a data analyst point of view is that there's a limit to how much privacy the data holder is going to allow. And so at some point that gets used up. So the way to think about it is that for some data analysis tasks, let's think of observational data. You go collect data from a big survey, you analyze it as many times as you want. But there's other data analysis tasks which are a little like landing or the rover on Mars, right? You can't do it a whole lot of times and see how it comes out. You do it once, you get one shot, right? And so you plan it out, like the vaccine trials that we're watching. Each one of those was planned out, presumably very, very carefully. I hope they were planned carefully, but they can't do it multiple times. Like each one cost about $2 billion. So you have to be very careful ahead of time. So what differential privacy does is it takes the first style of research and it actually turns it into the second. So you have to plan a lot about what you're doing. You don't want to run a lot of statistical techniques that waste the privacy budget on things you don't care about. So that's the story. That's the most annoying part of differential privacy. But there is no way, we know that there's no way around it and also protecting privacy. So good. Differential privacy, however, very interestingly, does seem to satisfy regulators, not only in the US, but around the world. The regulations are in place to protect individual privacy. This mathematically protects privacy. And so it should therefore make things possible in data sharing that was never possible before.
It sounds like we'll just have to, in using this, think about collecting data in a different way. Instead of doing the large surveys like you mentioned, do more targeted surveys that address maybe very local or specific questions.
Yeah, I think that's right. I mean, I think large scale surveys, if you ask 1,000 questions, or forget that, if you ask 100 questions, then the information you have on anybody is so detailed that it would be very easy to re-identify somebody. So that's harder to obscure. So yeah, so if you don't need 100 questions for a particular analysis, maybe we should ask fewer, right? So yeah, so it does change the way we think about data analysis, which is interesting. So there's a new problem, however. The new problem is that the differential privacy algorithms add noise, and noise to results is basically the equivalent of measurement error. And running analysis with measurement error that you ignore actually creates bias and inefficiencies. And those are statistically invalid. You can get the wrong answers, the wrong sign, the wrong size, the whole thing. They produce unknown statistical properties and no uncertainty estimates. So basically the people doing differential privacy are computer scientists, they just don't think that way. And so what we've been working on, my group has been working on, is fixing that problem. Because once we have that problem fixed, we can protect the individuals, we can provide insight about patterns that we're interested in, and we can do it in a statistically valid way so we don't ruin the science as well. So let me give you a feel for this, about the differential privacy and inferential or statistical validity, which is the key thing here. So here's the theory of inference of statistics and computer science. And they're actually very different. And it took me a long time reading the literature to really have a feel for this. But so let's imagine a population here of people where this is, by the way, Jonathan and Michael and Tim and right, this is all these guys, right? So and the whole population of all these people. And let's suppose the mean income is $48,000, which is about right nationally. Then we take a sample and we actually get to know the values for each of these people. And then there's a whole lot of people, of course, where we don't sample, so we don't know what those are. And these are the values, and of course these are unknown. The average of the sample is not the thing we care about. That's the important thing, right? The average of the population is the thing we care about, not of the sample, right? If you ask people, who are you going to vote for? The answers are irrelevant. They're only relevant if they're useful for the population we care about, which is the outcome of the election. And so we use this to infer to here, right? And that's basically what statistics is. We do statistical inference, which is using data we have to learn about data we don't have. And that's the whole thing of statistical inference. Okay, now let's worry about the fact that all this information is private, okay? So if that's private, what do we do? Well, the way I'm going to do it graphically is I'm going to imagine those numbers become embarrassed and they all turn red, okay? Come on, that's a pre-programmed joke, isn't that great? Okay, so now we're going to make those private numbers private, right? Those sensitive numbers private by adding noise and censoring them in particular ways. That's what differential privacy does. I'll show you how that works. And then we have another data set which has these, but with noise added to it and censoring. We basically messed with the numbers. Okay. In this data set, you can show to people and they can't violate anybody's privacy. So here's the inferential goal of statistics is to use these data to learn about the population. The inferential goal of computer science before you do noise and censoring is here's your database. You want to know something, you do a query, you get an answer. You want the mean, you get the answer. That's it. That's the whole thing. There's not much. It's not very complicated, right? You want to know the number of people that do something, you just count them, right? They do queries of their database. But in this case, we now have added this data generation process with noise and censoring, quite analogous to a sample. You know, it depends on how you sample, right? So we're starting here. We get to a differentially private data. And now we have to get from here, which is totally irrelevant. We don't care about this. It's got noise and censoring and it's messed with. And from a computer science point of view, we have to get back to here, back to the database that they would have had if it wasn't messed with. So that's what they care about. But as statisticians, as social scientists, we don't care what's in the database. We don't care what's in your sample. We care what's in the population that we're trying to make an inference to. We couldn't collect all the data from the population. We always have some type of error in collecting or limited information about the population. And so the computer scientists want to make an inference back here, whereas what do we want to do? We want to make an inference all the way from here to here. So we need to put some corrections in place so that we can take the differentially private data, which we know for sure, because the computer scientists have proved all the theorems that will protect individual privacy. But to get from here all the way to here is a new thing. And that's what I'm going to work on. That's what I'm going to tell you about today. Okay, sound good? Okay, great. So differential privacy and its statistical or inferential patterns. In classical statistics, what you do is you take a data set, which I'm going to call D, and then you have some function of it, like a mean, and that's your statistic, right? So it's very simple. You just take the data, some function of it, that's your statistic. In differential privacy, it's analogous to that, but not quite the same. Instead of a statistic, which is a function of the data, you have a mechanism. And the mechanism is some statistic and the data. And the idea, and then what you do is in the course of calculating the statistic, you add noise, and if numbers are too large, like if an individual might stick out, you censor it down, right? And that protects the individual privacy. That's fine, it protects individual privacy. The noise and the censoring are essential components of that privacy protection, but they are fundamental problems for statistical inference. We have to really be careful about that. Sorry? Oh, okay. Yeah, so the difference, so let me give you a feel for this particular standard. What's the standard? Well, the differential privacy standard, simplifying this, is the following, okay? So we have a data set with you, and then a data set without you, and we're gonna run an analysis. This is the probability of running this mechanism, producing result M, whatever that is. And this is the same, the denominator is the probability of running that same analysis with the same data set with one line deleted, your line, that one line, and getting the same results. If you got the same results for both of them, then it doesn't matter whether you're in the data set or not in the data set, whoops, sorry, and your privacy is protected. So that's the key. We want these probabilities to be very close. And what differential privacy says is they are so close, they are within epsilon of 1. So epsilon is how much privacy we're going to leak. And we'll keep epsilon small, so it's not enough to violate anybody's individual privacy. Everybody understand that little equation? There's only a couple equations in the whole talk.
Gary, can I ask you a question? Hi,
Sure.
I'm Colleen Strawhacker. I'm a program officer at the National Science Foundation. I do not like equations, but in the Arctic, we work with very, very small communities. So I've also been a proponent that like de-anonymization never works in the data that they work. So I'm wondering in these equations, if there's kind of like a minimum population size that this works for?
Yeah, so clearly if there was one person, there'd be nothing you could do. Then if it's a small community, then we have to figure out how big is it, exactly what we want to protect, because the community, of course, would be okay with communicating some information community-wide. It's not good enough. Your insight, I think, is exactly right. De-anonymizing wouldn't help. Also, aggregating the data from the community wouldn't help in many cases because it's such a small community. But in some cases, we can aggregate the information and also add a little bit of carefully constructed noise to protect that information and still get enough insight out so that we might be able to change public policy to improve the lives of the people in those communities. So while you can't do de-identification, you could do differential privacy. Depends, of course, on lots of things. But go ahead,
Okay,
Colleen.
I believe you.
But the principle here, the idea of the equation is, if I want to analyze your data and you're convinced that I'm going to get the same results, whether you, or essentially the same results, whether you give me your data or not, then you might be more willing to give me your data, because there's no question I could ask that would produce different enough results to reveal what your data say. You see that? Okay. So then I'm going to give you some examples of how to achieve this. And the way you achieve this is to define a mechanism that has this property, right? So what do you do to calculate your statistic? Okay, I'm going to give you, this is my second and almost last equation. So instead of calculating, for example, the mean, we're going to do the following. First, this would be the mean, 1 over n times the sum of y, except now we're going to censor this. We're going to censor y at a particular value. Lambda. Lambda is going to be a chosen value. So if we're calculating mean income and Bill Gates might be in the sample, then it's going to be really hard to protect him, right? So what we're going to do is we're going to say, you know what, we're not interested in income anymore. We're interested in income up to $200,000, and we're going to censor everything there. So that's one way of protecting him. But that's not enough. It turns out to make this mechanism differentially private, we censor some of the values. And then also we have to add noise. So this is normally distributed noise with mean 0, so it doesn't bias things one way or the other. But how much noise do you add? Well, this lambda is the same lambda as over here. So you choose how much noise, how much censoring there is. If you make lambda really big here, there's not going to be much censoring, which is good because that's what you want. But it's going to be big here, so it's going to add a lot of noise. If you make lambda smaller here to reduce the noise, then you're going to censor more. So it's sort of, it's a Heisenberg uncertainty principle. It's sort of evil, you know. To your point, Colleen, n is in the denominator here. So n is the number of people. And if it's really small, then this thing is bigger. If it's really big, then this thing is smaller. It makes sense because if one person is submerged in a sea of 300 million people, it's easy to protect them. So we have to recognize that, and it's recognized here. And then epsilon is the amount of privacy that we're going to protect. And so if it's smaller, then and therefore we're going to protect things much more, then this whole thing gets bigger. So that's a feel for one statistic, the mean. I'm going to use this equation again. Okay, but there's plenty of other ways of doing it. It's not only the mean. There's all kinds of other statistics that can be protected in different ways. The statistical properties, however, as they come out of the differential privacy literature, are usually biased. They don't have uncertainty estimates, so sort of a bummer. Okay, so now I'm going to describe a general purpose algorithm. General purpose in the sense that you can run whatever statistical procedure you want, and you'll get statistically valid results. Okay, so here's our estimator. I'm going to do it by analogy. You got a loaf of bread there. Okay, so that's your data set. I'm going to slice up the loaf of bread. All right, so I'm going to take different pieces of it and put them in different places. And so each one of these is going to be analyzed in a separate place. So we're going to partition the data. There's one step here called the bag of little bootstraps that's going to make things a little more convenient. Basically, the idea is instead of just analyzing this data, I'm going to analyze the data here, 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 and here, and then I'm going to average the results at the end. And it turns out by doing that, we're going to be able to protect privacy in a way that I'll show you. But if you calculate some statistics, what will happen is you can't just average them together. If you're calculating a variance, the variance is bigger just because you did the partition. So the big little bootstrap sort of fixes all those things. So you can just think of this as a fix. I'm going to skip it, but just so you know it's there. Then from this, you need to estimate something that you care about, some quantity that you care about. And I have that portrayed as a nice little sandwich. And if you're a statistician, a sandwich estimator is a really hilarious joke. So I can see you all laughing really hard. Okay, then the big values, like if big Bill Gates winds up in one of these and its income, you censor them so they end up smaller. The goal really is the average of these. That's what we really want, okay? But we can't see it. That's why these are red. We can't see them yet because we have to do our differential privacy thing, add noise and censor them. So here's censoring. We're going to average the censored values. This is not the thing we care about because it's got the censoring, so it's biased. We really want the average of these, not this little half sandwich. So what do we do? Well, we're also not allowed to see this because we haven't added the noise yet. So let's add the noise. We add the noise and we get something completely different. This is certainly not the average of these things, all right? Note the analogies. These are not exactly mathematical equations. But the noise, once you've done censoring and the noise, they have proven that you may then make this available. And that's great. We can protect everybody's privacy, but you're going to mess with the results we get. So if you conclude that this is the average of these, you're going to get the wrong thing. So we're then going to do a bias correction and we're going to do a variance estimation. Okay, let me just do this a little more formally without the bread. So we're going to put a D on here. That's my data set. Then we're going to have D1 through D5. Those are our partitions of the data set. I'll get rid of the bag of little bootstraps. Our estimators will be called thetas. That's usually the unknown. And then what we care about is the average of those thetas. And then we're going to censor, and we're going to average, and we're going to add noise. And I'm going to use exactly the same equation as I showed you on the previous page. Except instead of having the data in here, I'm now going to have these 5 things in here. So if one of them gets too big because Bill Gates was in there, it gets censored by this value lambda that we choose ahead of time. And then this is the normal added on the end. So this whole thing is the same, except these are the partition estimates instead of the individual data. And this is P, the number of partitions, rather than N, the number of observations. Why are we doing this? What is this all about? What this is all about is that this enables us to run any statistical procedure we want. And this is the result of it. So the statistical procedure could be a mean, it could be a variance, it could be the causal effect of something on something else. It could be an estimate of the number of things that we see. Any statistical procedure that is of interest could be in here. And then this protects its privacy in the same way as on the previous page. Okay. All right, so we have this, that's the same equation. All right, so this thing is the thing that this produces. The problem is that it's biased because it was censored and it's got noise added to it. So how do we fix that? So I'm going to show you how to fix that. How do we fix that? First thing is we take these estimates, 5 estimates, 1 from each of the partitions, and we plot their distribution. We actually know their distribution's normal because of the central limit theorem. The middle of this distribution is the true value, the thing that we really care about. It's going to be theta. And so that's what we really want to know. This thing is distributed normally, mean theta, variance sigma squared. That's what we see. Unfortunately, that's what we would like. Unfortunately, it's censored. There's a censored distribution. This is what we actually see. We take anything larger than theta and we lump it up here. So it just appears there, and that's all we see. So if Bill Gates's income is way the heck out here, it just gets reported at $200,000 right here. That's it. And so instead of this, we're getting this. We're getting the mean here. So that's not very good. We're going to have to figure out how to correct from here back from the censored value back to here. How are we going to do that? Well, let's label this. This area is just the integral from here forward. It's just the area under here. And then I'm also going to label this piece. So this piece is merely a weighted average of 2 things. It's a weighted average of the mean of the truncated area, not including this spike, and the spike. So it's a non-spike and the spike, and that's what it is. Okay, so now what does that give us? It gives us 2 equations, but 4 things that we don't know. So if you have 2 equations and 2 unknowns, we can solve for what we care about, which is theta, but we have 2 equations and 4 unknowns, we're cooked. However, we can disclose this one, because what does disclose mean? Well, if you use this equation, we're allowed to show that to people because it's differentially private. They're allowed to see that. So we show that to people. This is a differentially private version of this, which is biased. So we have to correct it, but in any event, one of those is gone. Next thing we'll do is we will disclose this. That's great, so we disclose that. So now we've disclosed 2 of them in a differentially private way with the appropriate noise, so it's not, nobody's privacy is violated. So now we have 2 equations and 2 unknowns, and we can get back to the thing we actually care about, which is the estimate of the thing that you sought to estimate. Okay, so forget all this. Suppose you had a data set and there was no privacy constraints. What would you do? You would have some kind of statistical procedure and you would estimate some kind of thing that you care about. What we're going to give you is the same thing, only it's going to have a little bit more noise, and you're still going to get standard errors. That's what this procedure does. Okay, we're going to get a way to estimate the variance, because the components, we're basically going to take these 2 things, we'd like the variance of them, we're going to draw them from a normal distribution where the parameters are functions of all the disclosed parameters, so it's not hard to do. Each simulation gets bias corrected, so we get lots of the values of this, this is the bias corrected value, and then the standard deviation of this over simulations is our standard error, and the bias correction at the end of the day, which is the thing we sought to do, reduces the bias, of course, and it reduces the variance also. So it eliminates some of the noise that was added, and it eliminates the effect of the censoring. So that when we do our analysis of some big problem, when we look for social science patterns, we can find them and it won't mislead us. So that's the general idea. Let me show you the way it works in practice, just to give you a feel for it. These are simulated values, but they work in reality too. So along the horizontal axis is this alpha. So it's the area that's being censored. So over here, there's very little censoring, and over here, there's lots of censoring. So the differentially private result that the computer scientists said you should just make available because it doesn't violate anybody's privacy is the orange one here. And unfortunately, the more censoring, this is 0 bias and down is more bias. So the more censoring, of course, the more bias there is. You know, if you have Bill Gates' income in there and you censor it down to $200,000 and you take the average of that, you're not going to get close to his income. And so the more censoring, the more bias. And so our bias correction basically always produces 0 bias, regardless of what it is. Okay. This shows it doesn't matter what the sample size is, although for Colleen, this particular example only goes down to 10,000, so we'd have to be careful with your sample. I didn't sample for that. And this is how much privacy protection you're willing to give up. This is a lot of privacy protection. This is not as much privacy protection. If you do it the usual way, you get lots of bias. If you do it our way, you get no bias. And then finally, we have to calculate standard errors, our uncertainty estimates. A scientific statement is not one that's correct. It's one that comes with appropriate uncertainty estimates. And so this is the estimate of the standard error, the uncertainty estimate from the differentially private estimate from the computer scientists, and it's over here. These 2 are from our estimate. One of them is the truth, that's the truth. This is our estimate. So first thing is our estimate is near the truth. That's good, that's the whole idea. So we're getting the standard error right, the uncertainty estimates are correct. And then secondly, both of these are lower than the computer science estimate. So by doing the bias correction, we actually not only reduce the bias, but we also reduce the variance, which is a good, useful thing. And then because I really like these graphs, I put them all in the same place, and I show them to you again. For no particularly good reason, except they just look so cool. Okay, that's mostly a joke. Okay, final comments. So we're going to change from the data sharing regime to the data access regime. We're going to differential privacy will protect individual privacy mathematically, absolutely. One more comment for Colleen: if the data set is small, what will happen is individuals absolutely will be protected no matter what. You always protect the individuals, but it may be that we just can't learn as much, right? That's the deal. It enables inferences to a private database, not to the population when you do it in the way the computer scientists were suggesting. It is usually biased with no uncertainty estimates and fails to protect society from scientific conclusions that are wrong. And so instead, we're going to add to the differential privacy literature inferential validity. And as I said, a scientific statement is not one that is necessarily correct, but it must have known statistical properties and valid uncertainty estimates. And that is what the methods that the general purpose generic methods that are privacy protecting that we're describing here do. The proposed algorithm is generic, works for any statistical procedure. It is unbiased and has lower variance, has valid uncertainty estimates. It's computationally efficient. That is, because you break the data set up into different parts, it can be run much faster than a gigantic data set in one computer. It's one of several examples I showed you of solving political problems technologically, which I hope we can do a lot. There's lots of problems of our communities working together and finding technological ways of avoiding the problem of collaboration rather than having to balance one or the other is something I think we should really pursue. And then we have several implementations in progress, one by Facebook and one by a collaboration we have with Microsoft and Harvard at the institute I run called the Institute for Quantitative Social Science. And there's also an open source project called OpenDP, which I'll just tell you about for a second. So all this great software that's going to protect privacy absolutely of every little community and also make it possible for us analysts to learn about the general patterns. If I implemented that in code that nobody could see, like what is that? That would be useless, right? Because like that code could like have a leak out the back. So the only way to really do all this is to have open source software that implements all this, that the community checks and vets and verifies, and it becomes a trustworthy set of software. And so we have a big project with lots and lots of people involved to have one focus of effort from the whole differential private community. Okay, and that's me and my co-authors, and I'm happy to take questions or comments or whatever it is you might like to talk about. So.
Great, thank you very much.
Thanks.
Yeah, I have a few thoughts, but I've already spoken. So what I'm really interested in is hearing from IARPIC and how this, like Colin was saying, how this might apply in the Arctic.
This is Mike. Can I jump in to start us off? For Dr. King, thank you. I really appreciated the sandwich equation that helped me and also reminded me that I skipped lunch. Thank you for that. So two quick comments and then kind of a comment / question. Spatial data. But clearly, you know, you can do, there's an issue with privacy of, say, ship tracks. Not everyone wants to know location. That's part of, you know, the privacy, data privacy challenge with access to ship tracking data. So I imagine there can be, this kind of approach can be applied to spatial data to kind of cause noise in the spatial location, then be able to kind of derive it when you need it, if you have the key, if you have the equation. Second comment, wondering about how, so in the spatial data infrastructure world, to try to get better access to spatial data, this idea that's emerging as a potential key to free up private industry data, as a proprietary aspect to this, is to create derivative products that can't be reverse engineered to get the original source, because private companies want to protect their data. They don't want it just out there, but if you create something, you add value and free it up to disseminate, you take away that risk of the private industry sees of getting the data, so you can kind of sell it and continue to develop their product. Wondering your thoughts on relationships, if this is a potential, if you're seeing that the community that you're working with, private industry mostly, it sounds like, are thinking about applications for like government data, in that way, protecting private industry, you know, financial interests. And also a general comment / question. I'm wondering how this is all being, clearly huge implications for freeing up all kinds of data, census data, you have lots of different audiences, lots of different decision makers that are going to assess the risks. So I wonder, you know, IRBs, Institutional Review Board, how do you see them, you know, understanding this enough to be able to do that risk-benefit analysis. Governments, different agencies, you're going to have to, there are many gatekeepers, different controllers of different data sets. So worry about the status of socializing this key and what's the prospect going forward.
Okay, so those are great questions. They cover lots of things that we're working on. So first of all, differential privacy is relatively new. It's totally taken over the field because everybody understands that this is pretty much the only way people have shown to get everybody what they want: privacy protection and scientific, accuracy. But each data set that you analyze, or each type of data set you analyze, requires different differential privacy and then different statistical corrections. And spatial data is an interesting one. Folks are working on that. And so that is absolutely possible to do. There's no off-the-shelf way to do it right at the moment, but if you had a particular data set, we could work together. We could try to figure out what that might be and develop the methods necessary to make that available. You have to understand precisely what needs to be protected. Is it a particular ship? Is it, or is it the people on the ship? Exactly what it is. And then what kind of insights might you want from those data? So that's a great example. There's lots of, you can imagine there's lots of specific types of data. My guess is not only in the world, but that you have access to: time series data, count data.
Colleen's mentioning in the chat the archaeological record. Sites that have historical significance that we don't want people to go raid, so we don't make that information available publicly.
That's a great point. So then the next question, so one is you just keep it secret, but the next question is, would there be value? Like if an analyst had access to that, aside from using it to go do something bad, would there be something useful to do? Like maybe the distribution of archaeological sites are higher over here rather than here, and so we should hunt over there rather than over here or something. If that's true, then we could absolutely protect the location while making it possible to analyze the data. But that's another good, interesting type of data set that we could go after. But to continue on Michael's point, the talk that I gave today was about differential privacy about the results, right? So you run an analysis and you run any statistical procedure you want and you get your results, okay? There's another way, which you mentioned, to protect data, which is you take the data set, you add noise and censoring to the data set, and then you make the data set available. The Census Bureau is actually doing that for the 2020 census. So they're all in on this, and all the lawsuits are about to start. But intellectually, it's absolutely the right thing. And they're going to be protecting privacy way better than the census has ever protected privacy before, and we'll still be able to learn from it. But the way they've decided to make data available is to add noise to the data set. That feels better for the analyst because we can run as many, epsilon has already been spent on creating the data set. And so the analyst can run as many procedures as they want. So it feels better. On the other hand, if you knew exactly what you wanted, you wouldn't disclose the data set, you would disclose those things, and then you could learn more about it because you could spend the privacy budget in better ways. So there's always these trade-offs, which is fine. But yes, I think that's likely to be the way to make data available in a lot of situations. With Facebook, we made a data set available on all the URLs clicked on Facebook, and then whether each URL was a news story, and if it was a news story, whether it was misinformation, whether it was judged as fake news and things like that, and which types of people were clicking on it. The data set has 17 trillion numbers in it. Like that's actually real. So that's a big data set. But what we did is we give access to this data set rather than to the results. And that means researchers can run as many analyses as they want. Finally, your last point, which is also really interesting, is, oh gosh, you got a lot of negotiation ahead of you, right? And that's absolutely right. One thing, the organization I mentioned that we set up for Facebook is called Social Science One. And what we're doing right now, essentially in response to the idea behind your point, is we're restructuring that to be an association of social science research centers. So we're going, this is not public yet, but we're going and signing up lots and lots of social science research centers because the Facebook project, I thought it was going to take a month, and it took 2 years to really have the data flow. And yes, I experienced all the difficulties that you described and lots more. But we learned a tremendous amount in the process. And when we tried another one with Microsoft, it was way easier. When we tried it with others, it was way easier. And now lots of people come to us and say, how do we work with this government agency? How do we work with this company? And not that we know the answer, but we have lots of examples. And so it makes it easier. So yes, we need a flow of information so that we can make these negotiations easier. And then if you know that some other group is doing something and you just want to do it the same way, it'll be much easier for you politically as well. So
there was another question. We're getting quite a few in the chat. Alan Pope raised a question I had myself when you were talking. It really aligns to the way in the physical sciences that people are moving their compute to the cloud. So they're giving Amazon or whatever the code to run, and it's changing the model. It's also like how they do it with supercomputers, but in a sense, it takes the compute responsibility away from the PI and puts it on a central organization that has the data. So that has really interesting implications for, as Alan was mentioning.
yeah, I think that's right, because eventually, I mean, right now it's possible to take, small universities or small research groups or small offices within the government and give them a server without building it, right? You can spin it up on Amazon. It's really easy, or Microsoft or whatever. But what we're going to do, where we're going, is eventually that will also have privacy protection bound up into it. And so you could give somebody one of these servers, just spin it up on their browser, and everything will be easier. So I wanted to take a little liberty here and introduce my stepdaughter, Anya, who joined us, has been an Arctic policy enthusiast from when she was an undergraduate. She's a graduate student at Georgetown at the moment. So thanks for the indulgence.
And for letting me join in. I'm just interested in the geopolitical implications of the Arctic, especially as it relates to Russia. So I was interested to hear your talk today, but nice to meet you all.
You should definitely join IARPIC. We're having a lot of interesting conversations on the topic that you're interested in.
Cool.
Well, I think we're coming up on the top of the hour. Just reading Jeffrey Brooks's question. Oh, he said he had to go. So I think we had all our questions answered. So thank you very much, Gary.
Okay.
Thanks, Timothy, for introducing him. That was excellent, as I anticipated. And thank you to the IARPIC team for joining us today.
Thanks, Gary. Great talk.
Thank you so much for joining.